Welcome back. We're chugging along in Module 8 talking about interpolation and spatial statistics. Last time I talked about kriging. Remember, that's the interpolation method that uses statistical approaches. There are a lot of assumptions you need to meet to be able to do kriging well, and if you've met those assumptions, then you'll be able to do a really good job of interpolating. Earlier in this module I gave a little summary of traditional descriptive statistics, and those of you that were paying attention remember that I went through all these different descriptive statistics, but they're all traditional. Notice that they all deal with the values of the data, but there's nowhere in there where they're dealing with the geography, the location of the data. So we need a way to do statistics that help us understand the wheres in addition to the whats. And that's what spatial statistics will help us to do. Okay, just like in traditional descriptive statistics, we have spatial descriptive statistics that help us understand where the data are located, The mean center, central feature, median center, standard distance, and directional distribution. There's also an average nearest neighbor descriptive statistics that I'll talk about a little bit later. Okay, so what the heck is the mean center? Well, the mean center is what it kind of sounds like. It's the average coordinate of all of your data, the where average of all of your data. So you average all the x-coordinates of all your points, or if you have polygons, you might average the x-coordinates of the centroids of the polygons. You average all the y-coordinates, and the mean center is at x average, y average. So that's the mean. Here we have a graphic showing Utah with all of the genus. Remember, genus is the data that comes from the Census Bureau of all the places that have been defined in Utah. And realize here that this graphic of Utah, notice it's got right-angled corners. It's kind of a square, blocky Utah. And that should trigger something in your mind from way back in this course when we talked about projections. And this is very likely a geographic projection, and that's not going to work very well when you use anything that involves calculations or distances. So just a warning, you should always be using projected coordinates. I'm not doing it in here, but you should always be using projected coordinates when you do these calculations. Okay, so where's the mean center of Utah? It's that red X there, or red plus. That's where the mean center is. Median center, what does that do? Well, you get an input of all your points, and it finds a point that minimizes the distance between the point and all the points inside of your data set. So it's creating a new point that's closest in total to all the points. So you can imagine lines going from this point out to each of the other points, and the distance between this point and all the other points is minimized. So what do? We pick a point, we calculate the total distance to all the other points, pick a new point, calculate a new total. The point that comes up with the smallest total distance is going to be your median center. What's that? Here's Utah again, same points. Here's Utah median center. This one's an X. Central feature. Central feature takes your input points and picks the single point in your input data set that is the minimum distance to all the other points in your input data set. So remember, the median feature calculated a new point, it created a new point. The central feature is picking one of your existing points and picking the one that's the closest to all the others in total. For each feature, calculate the distance to the centroid, or if they're points, just to all the other points. Sum the distances. The smallest total is the central feature. Standard distance. Standard distance should make you think of something kind of like standard deviation when we're talking about traditional descriptive statistics. And if you look at the equation down here, you can see that it's pretty similar. This is like a variance in the x direction, where you take the value of each x coordinate, subtract the mean x coordinate, square it, divide it by n. You do the same thing for the y coordinates, sum those up, take the square root, and that's the standard distance. So in keeping with what traditional statistics would say, if the data were normally spatially distributed, then one standard distance would enclose about 68% of all your data. Here we have Utah, and here we have standard distance. So if these points are normally spatially distributed, this circle is going to enclose about 68% of the total points. Two standard distances would go up to 95, and that's the way it's same as in traditional descriptives. Directional distribution, that one's going to take into account the fact that sometimes there's a directional trend in your data, and it's going to separate the X and the Y variances and distributions and come up with an ellipse instead of a circle. So in this case, with this example, you can see that there seems to kind of be a tendency for the points to fall in that direction, and you can see that your directional distribution looks like this. So what is it doing? It's splitting what the standard distance was combining, so it's got an X and a Y direction, and based upon those values it's going to come up with an angle that gives you an ellipse, and you're going to be able to get a semi-minor and semi-major axis, and that gets you the size of the ellipse. If we look at Utah again, here we have the ellipse, and you can see it's kind of stretched out vertically, and it's kind of compressed horizontally compared to the standard distance, and it appears to have a little bit of an angle away from true north-south. Okay, so this is the summary of all those things. You can't really see the central feature, but it's a tiny yellow point there that's real close to that median center. And then we have standard distance, we have directional distribution. Okay? Like I warned you about earlier in this video, you can do the calculations using geographic coordinates, and you can do them using projected coordinates. If you use geographic coordinates for the mean center, you get this point. If you use projected coordinates for the mean center, you get this point here, and you can see that there's a 2,000 foot difference between those two calculations. So if 2,000 feet, which is almost half a mile in this case, makes a difference to you, make sure you don't use geographic coordinates, use projected coordinates. Okay, average nearest neighbor. What that's going to allow you to do is determine whether or not the points are clustered more or less than points in a standard normal spatial distribution would be. So in a standard normal spatial distribution, some of them would be close to each other, some of them would be far apart. In a clustered distribution, you see again clusters, and in a dispersed distribution, they're all kind of equally far apart. So the average nearest neighbor is the average observed distance between each point and its nearest neighbor divided by the expected observed distance between each point and its nearest neighbor. So the observed, you add up all the distances for each point between each point and its nearest neighbor divided by the number of points. And for a standard normal distribution, the expected is 0.5 over the number of points divided by the total area of your study area. So notice the study area is going to be important. Okay, so here we have average nearest neighbor, and what we get out of that calculation is an observed average distance, 960 meters. If it were normally distributed, we'd expect 2,350 meters. So things seem to be more clustered than they would be in a normal distribution. And since this is an inferential statistic and not necessarily a descriptive statistic, you're going to be able to run a test on that and come up with a z-score. And remember how you do that from the traditional descriptive statistics. If you fall far enough from the mean, you're going to be able to make a conclusion that standard normal distributions do not apply. So in here you can assume standard normal distributions apply. The further you get away from the mean, the less likely that the standard normal distribution applies. In this case for Utah, our z-score is minus 200, and if you look at this chart over here, anything less than minus 2.58 is less than 1% likely to be random, and so you can see that Utah is clustered, and that's what that's going to tell us. Okay, so we've got all these measures of data location that we can apply. And this is an example of the mean center, right? Add up all the x coordinates, add up all the y coordinates, divide it by the number of points, and you get the x and y average coordinate. We can also do weighted, so we can take into account not only the wheres, but the whats. So you can imagine, let's say we had population and we had 100 people at one point and 10 people at another point. The way that the calculations work is they in effect make 100 points right on top of each other at the place where the population is 100, and they make 10 points on top of each other right where the population is 10, and they do the calculations as if there are 100 points in one location and 10 points in another location. It gives them a completely different result in terms of what those locations are. So you can do combination what and where to give you weighted descriptive statistics. Here's some examples of the United States. We have the conterminous or contiguous United States, that's red, and we have the 50 states, and that is green. And so when you take into account Alaska and Hawaii, you can see that the mean moves to the west, and it turns out to move a little bit to the north because Alaska is way up there. Okay? When you do that for the median, and remember the median is going to do distances to these places, distances to the centroids. The mean is just going to do averaging coordinates. You can see that the medians for 50 and CONUS are roughly the same, or they're much closer to each other. And that in general is going to be what happens, is the mean is going to be more sensitive to outliers. So in this case, Alaska and Hawaii are outliers, so the mean is going to move further when you have outliers included. When you use the median statistic, the outliers aren't going to have as much impact on that statistic as the mean. Okay? Here we have the weighted mean, and the weighted mean is going to take into account the populations of the states. Okay? So the CONUS mean versus the 50 state mean, and you can see that, no, just the CONUS mean versus the weighted mean, and the weighted is in the yellow. So there's more population in the southern part of the country, and so that pulls the weighted mean away from the spatial mean. If we look at the median, you can see that the median gets kind of pulled in a different direction because of the higher population in this part of the country as opposed to just averages over here. And so the mean is pulled in one direction, the median is pulled in another direction. You're going to get different locations for those points. So depending upon what you calculate, you're going to get different locations. And from those things, you're going to be able to determine or infer that there's something going on with the wheres and or the whats for your data. So next time I'm going to talk a little bit more about some inferential statistics that you can use to kind of hone in on what's going on in terms of, is your data clustered in terms of where, or is your data clustered in terms of what? So that'll be next time.